ಈಗ
Good morning, everybody.
Hello, sir. Is it audible to you, sir?
Yeah.
Yes, sir.
Yeah, ma'am.
Thank you.
ಒಂದಿಷ್ಟು ಮಾಡ್ಕೋತಾಳ ಅಂತ ಅಂದ್ಲ ನಾನೊಂದ್ ಕಿಲೋನೇ ಕೊರದ್ ಹೋಗಿದ್ದ ಬಂದ್ ಚೇಂಜ್ ತುಂಬ್ತೇನ ನಿನ್ಗೊಂದ್ 2 ಕಿಲೋನೇ ತದಾವು ಚಲೋ
Good morning, ma'am. Jyoti, ma'am.
Yes.
Shall we start, ma'am?
Yes, ma'am. Go ahead.
Okay.
Good morning, sir.
Yeah. Good morning, ma'am.
Good morning.
Good morning, all of you.
Yeah.
A very good morning and warm welcome to you all for this one-day national seminar on boron in cluster chemistry and catalysis, organized by Department of Chemistry in association with IQAC, K.L.E.S Raja Lakamagowda Science Institute, Autonomous, Belagavi. Now, I request our beloved principal, Dr. Jyoti Kavlekar, ma'am, to welcome the gathering. Over to you, ma'am.
Thank you, madam. Yes, a very good morning to all of you. I'm very delighted to welcome you all to the national webinar on the topic Boron in cluster chemistry and catalysis, organized by Department of Chemistry in association with IQAC of our college. Okay, let me say something about our esteemed K.L.E. Society. Our K.L.E. Society was established on 13th November 1916 by 7 dedicated teachers, whom we call them as Saptarishis. Initially aimed at providing basic literacy to the children of the farming community, but today it has grown into an amazing educational organization of 270 plus institutions. The destiny of any institution unfolds according to the choices an institution makes in its leadership, and such a choice was made by the institution in the elevation of Dr. Prabhakar K.L.E.S. sir to the chairmanship of the Board of Management of K.L.E. in the year 1984. With his determined spirit and youthfulness, Dr. Prabhakar K.L.E.S. sir initiated a great transformation in the making of a new K.L.E. and not only enhanced the number of institutions of K.L.E. from just 38 but to 270. It has created a roadmap for the next generation to travel in. And among these 270 institutions is our K.L.E. Society's Raja Lakamgowda Science Institute Autonomous. Our college was established in the year 1935, and Sir C.V. Raman, the Nobel laureate, inaugurated the degree course in science in 1944. We are accredited thrice by NAT at A grade. Our college has started functioning as an autonomous institute from the academic year 2013. We offer 2 UG programs, BSc with 9 different combinations of subjects, and then we have BCA. Apart from these, we have 2 PG programs, 3 PG programs, MSc Physics, MSc Chemistry, and MSc Mathematics. And we also have several certificate courses. As per our vision and mission, we adopt holistic education concept and focus mainly on the quality education to achieve competencies to face the global challenges. We always want our students to get exposed to novel subjects so that their thirst for knowledge increases. Hence, always we go for new topics and new thirst areas. And in this connection, our Department of Chemistry thought of exploring about boron chemistry, a rapidly expanding research field. Boron, as we know, is the only element other than carbon that can build molecules of unlimited size by covalently bonding to itself and form boron clusters that exhibit an astonishing variety of stable architectures. Maybe to many students and teachers, such structures may appear strange and disconnected from mainstream science, yet exotic molecules, especially those whose structures surprise and puzzle the theory of the day, play an important role in chemical education since they force us to rethink our ideas of chemical bonding and reactivity. Students in particular need to understand that chemistry is not a static science with its basic ideas frozen in place. Rather, our understanding of fundamental concepts of bonding, molecular structure, and chemical reactivity is continuously evolving. In fact, it may happen so that entirely new field of chemistry can come into existence unpredicted by anyone. Chemistry, like other branches of science, is most exciting when it is expanding into unexplored territory. Hence, to know more about boron in cluster chemistry and catalysis, Department of Chemistry, in association with IQAC of a college, has organized today's national webinar. We have a very eminent speaker amidst us for this webinar, Dr. Shubhankar Kumar Bose, Associate Professor, CNMS, Jain University, Bengaluru. Sir, on behalf of our management, all the participants, entire faculty and student community, and my own behalf, I welcome you to today's national webinar, and at the same time, thank you for accepting our invitation to grace the occasion. I extend a warm and a hearty welcome to all the esteemed participants of the webinar. Hearty welcome to all the esteemed members of management. Welcome to Professor Nanjapnar, Life Member and Member Secretary K.L.E. and Dr. Satisha MP, IQAC and NAC Coordinator of our college and Life Member and Member Secretary of K.L.E. Welcome to the entire organizing team, all my staff and students. So I request all of you to make the best use of this webinar. Once again, welcoming you all, I conclude. Thank you. Thank you so much.
Thank you, ma'am. Now I request Dr. Lata ma'am to introduce our today's resource person. Over to you, ma'am.
Good morning, everyone. I am Dr. Lata M.S., Assistant Professor. Would like to give a brief introduction of our resource person, Dr. Shubhankar Kumar Bose. He was born in Sikar, India. He received his MSc in chemistry from the University of Rajasthan in 2004. He got PhD from IIT Madras in 2011, for which he has been awarded the Professor Warner Prize for his PhD thesis. Later, Dr. S.K. Bose joined for the postdoctoral fellowship from the Alexander von Humboldt Foundation and University Würzburg, Germany. Presently, he is working in the capacity of Associate Professor at CNMS, Jain University, Bengaluru. He has published more than 40 research articles in reputed international journals. I request to all the participants, put your queries in the chat box only. With this brief introduction, I once again welcome our resource person, Dr. S.K. Bose. I request to all the participants, put your queries in the chat box only. Now I'm going to hand over to our resource person, S.K. Bose. Sir.
Yeah, very good morning to all of the participants. And first of all, I would like to thank the organizing committee and particularly Principal Ma'am and Dr. Lata Ma'am for giving me this opportunity. So as Principal Ma'am very correctly mentioned that the boron chemistry, but today I'm going to show you two different class of chemistry. How they are standing together, and of course they are very much apart from each other. The cluster chemistry, which is, as Principal Ma'am also mentioned about that, it is very fascinating in terms of the bonding, and which leads to the boron cluster compounds. And another part which I'm going to talk about is the boron in catalysis, which is really very interesting and a kind of very emerging field, and a lot of good work is going on all over the world, particularly in Europe, US, and in China, and of course in Japan. So I'll just take you on this journey. So as my title of my presentation is Boron in the Cluster Chemistry and Catalysis. So first, I'll just show you how important the boron is in our day-to-day life. Then we will go into the chemistry, how their bondings and their applications in our research. So boron, as we all know, that it is a group 13 element, and that is only the non-metallic element present in group 13, but it has a quite similar properties like a near element, which is carbon silicon, and it makes the covalent bonding. But the boron is actually, you can find in the earth crust, and that was discovered in 1808 or so by Joseph Lewis, and later on English chemist has refined it and got this very pure boron, which I have shown is rhombohedral boron, elemental boron. So this boron, if you see and look back, earlier days in 19th century, when they found that boron can be very much useful, which I'm going to talk about it in next few slides, they found that in all over the world, the natural source of the boron are present in basically in Turkey, 45%, then followed by US and then Russia. In 19th century, they used to carry this borax. Always boron preferred to match or make the bonding with the oxygen because of its oxophilicity and always occur as a borax. So here you can see that how they used to carry in 19th century from the mining place to the chemical companies. And this is some of the images which are in the Turkey where they are mining, and in the town you can see there's a chemical company where they use this borax in different applications. So why earlier people start to think about this chemistry, and it has been expanded a long way, but during the Second World War, the chemist found that one of the boron compound, which is a B5H9 pentaboron compound, they found that it has a very specific property and they can use as a rocket fuel. And as we know that during the Second World War, there was a race between the America and Russia to produce more and more fuels. And during that time, they found that B5H9 actually can be useful for the rocket fuel. And successfully in 1960s, US has launched this Type 2 rockets using B5H9 as one of the component in the fuel. They call this exotic fuel and Green Dragon because it born in a green flame. But by knowing this, USSR, which earlier we called that, now it's in Russia, they mainly concentrate on B10H14 and they use also as a rocket fuel. But unfortunately, the research later on has been stopped. The reason was which did not realized by the scientists on that time, that when they burn this pentaboron or decaboron, they actually convert into the borax. And borax is nothing but it's a solid, unreacted compounds which block the exhaust of the rocket. And because of that, they stopped all the research related to the rocket fuel or on the pentaboron or so. And almost $1 billion US has been washed out, which they have spent or invested in this type of research. And almost hundreds of the canisters were lying till end of this 21st century because these borings are very, very explosive. So they have to find it out how to destroy it. And finally, they could be able to do that. So that was the main highlight during the World War, and they found that boron can be used for the rocket fuels. But in day-to-day life, if you see, very important applications the borosilicate classes. In more or less all the chemistry labs, even in the physics as well in the biology labs, whatever the glassware we are using are all borosilicate. And they are a bit expensive because it has because the addition of this boron trioxide give extra stability to the glass, and that is the reason we are using in our chemistry labs. You can heat it up; it won't expand it, and it can tolerate up to 150 degree or so. Or and in day-to-day life in the kitchen, and we can found that this borosilicate glasses. Another very important application, which probably some of we are not aware of that, is a boron nitride, particularly hexagonal nitride, which is a non-toxic compound, and it has an excellent lubricant property. And because of that, it has been used as an additive in lots of cosmetic products. And because of its non-toxicity, we can found that almost 10% this hexagonal boron nitride has been added in so many cosmetic products. And very important in terms of the application, wider application, this boron nitride, it's in aerospace, and that is because of its low thermal expansion and high temperature stability and good thermal insulator property, this boron nitride has been used to manufacture a lot of aerospace or the parts of the airplane. So next, the very important application which is recently emerged is a boron in steel. If you add or dock the boron in the steel, it gives extra strength to the steel. And basically, this type of boron steel has been used, or it's continues in the use in automobile company and in the construction. And here I have shown one of the leading sports car manufacturer company, Porsche, is using this boron steel to manufacture some of the parts of the sports car. And in terms of the application towards the medicine, the boron also having a very important application, which is we call this boron neutron capture therapy. And why it is important? Because we know that how the cancer is very dangerous disease. Moreover, the problem or the limitation of the therapy of the cancer is there are a lot of therapies are present, but when you use a different therapy or the chemotherapy or so, not only this therapy will destroy the cancer cell, but also the normal, the good cell also will be damaged by that therapy. That is one of the limitation. So researcher, what they found that if you use the boron 10, so here I would like to mention that the borons are in two isotopes, boron 10 and boron 11, and boron 10 is in 20% abundance, and boron 11 is 80% abundance approx. So if you use the boron compound, boron 10 enriched compound, and put it in the cancer cell, and you just thermally activated neutrons, if you bombard, it cleave into the helium particle and the lithium. And because the range of these particles are as small as a tissue, or it's around 9 mm to 5 mm, so it destroys the particular specific cancer cell only. And that was the main advantage of this boron neutron capture therapy for the cancer treatment. But still the research is going on. The main challenge, still people are trying to find it out how specifically you can keep or the transport the boron compound to the target cell, which is a cancer cell. Okay, so another very important application is boric acid, and I think we all are using that in some point in our life because it's antiseptic and antifungal and antiviral property, and basically it has been used widely and very cheaper way where we are using this boric acid to disinfect some of your wounds, and particularly for the eye wash as well. Okay, so from this, I would like to move on to the chemistry part. So from this, you can see that by knowingly or unknowingly, we are using boron products in day-to-day life. But from that, I'll just move to my talk, which I have divided into two parts. The first part is where I'm going to talk about the boron in cluster compounds. Very briefly, I'll talk about the bonding and some of the Waite-Swingos rules and boron cluster compounds, and my contribution towards this field as well. And the second part I'll talk about is organoborane, which is totally different from the metal cluster or the boron cluster compound, which is mainly focused on inorganic chemistry. And we'll talk about this application cis coupling reaction and how we can synthesize this organoborane compounds in more cheaper way. So let's start from the boranes and the boron cluster compounds. So boron, we all know that it is, as I mentioned, it's a group 13 first element, and the neighbor element is the carbon, nitrogen, and oxygen. And if you see the outer shell orbitals of this carbon, nitrogen, and oxygen, they have 4, 5, and 6 outer shell electron. And if they make the bonding between, with the hydrogen, the 4, 3, or 2, they will reach to its octet. And as we know that octet rule, that whatever the compound in the main group compounds, they prefer to reach their outer shell electron to the to up to 8, because once they reach it, they are very stable, they are very happy, and because of that, they all prefer to have this configuration. But when you see about the boron, boron has only 3 outer shell electrons. So you can see, imagine that only 3 hydrogen it can bond equivalently. After binding with the 3 hydrogen, still it will have one empty orbit, p orbital. And because of that reason, this boron become really showing very unusual structure, because it has a lack of electron. It's hungry towards the electron, so it want to fulfill its octet, and it's try to make bond with whatever it's nearby, whomever can donate the electrons to the boron, and which leads to unusual structures, and which we call as a non-classical bonding. And we will see that boron not only the 4, 5, or 6, or 7, it can go the n number of bonding to fulfill its octet. So basically, what we will concentrate today, that multi-center 2 electron bonding, which is very well known, which we call as a banana bonding. So this boron, as I talk about that, it's naturally occur. So this borax first in 1979, as Jones reduce it and react with HCl, they got this boron BS3. But the pioneer work is the contribution is given by Alfred Strock, and which actually come up with the shrink technique later on, and which reduce it and got a mixture of the boron compound, and he could able to distill it and get the pure boron compound. Here I have shown B4H10, and here you can see nice green color. When you burn the boron, and it will burn in the very nice green color. That's why it's called it's a green dragon. Because of this color. In laboratory, you can definitely can synthesize these boron compounds by reacting with the boron trifluoride and lithium aluminum hydride, which keep this diboron compound. Not only that, there are a series of reducing agents which can be used to react with the boron compound and keep the diboron compounds. Once you have these diboron compounds, by very precisely controlling the temperature and the pressure, you can convert or convert this diboron into the higher boron. When you react it at 25 degrees centigrade, it can convert into the arachno B4H10, as well as in high temperature, it convert into the beta H14 as well. So you can see the boron, which is naturally occur, can convert and come into the laboratory, and they convert into different boron compounds in the large scale as well. So if you see the bonding, as we saw that outer shell, it has a 3 electron. So if there is a Lewis acid nearby this BS3 or the boron, it try to make a coordination bond, and it will be happy to have an extra electron from the Lewis space. But if there is no Lewis space around, what they will do it? So what they are doing is 2 of the electron deficient BS3 groups will come together and share their electron to each other and become happy. And which leads to this banana bonding, 3-center 2 electron bonding, which we all know about that. And this bonding has been confirmed by the Lipscomb, who got the Nobel Prize in 1976 by the X-ray and electron diffractions. And here you can see the B2H6 have a 4 terminal and 2 bridging hydrogens, and 2 bridging hydrogens are basically involved in the 3-center 2 electron bonding, right? So when the larger number of borons come into together, it leads to the cluster, as I have shown that if you heat it up and particular temperature and the pressure, it leads to the higher boron. So now the problem was when the K.L.E.S found that there are a lot of borons around and they have been published. So how they can able to classify that. In that place, this weights Mingos coming rules coming to the picture. The weights and Mingos independently, they have given or they publish an independent paper on the polyhedral skeletal electron pair theory. And this theory is not only restricted to the boron compound, but also it can be applicable for the heteroboranes, metal boron compounds, and even boron-free metal cluster as well. And what they have mentioned in their paper that if any of the cluster having an n+1 SEPs, SEPs is here the skeletal electron pairs, having n+1 SEPs, here n is stand for the vertex, and vertex is nothing but having this corner of the cluster. Here I have shown one very nice example of dodecahedron geometry. So all these corners you can see they are called as a vertex. So if you have n+1 SEPs, then they classify those boron compound as a closure boron. When they have n+2 SEPs, they call this a nido borings. And when they have found that the electron count is n+3, they call this arachnoborane, and n+4 is called this hypsoborane. It's a closed shell. It's a nest type of structure. Arachno is a spider web, and hypo is like a net type of structure. So based on the structure, they bring all the boron compounds and put it in different class, and they have classified and they have given the nomenclature for that, and they have go to the molecular orbital theory, and they found the electron counts as well. So this PSEPT theory are very important to find it out the electron counts, not only for the boron, but also heteroboranes and even metal cluster compounds as well. Okay, so so from here I'll just show that what researcher have done. So we all know about the carbon and metal bond, which we call as organometallic chemistry, right? And which is very important field in the organic and inorganic chemistry as well as in industrial importance. So similarly, when there is a bond between the metal and boron, we call it metal boron compounds. And they also have been recognized by the group of the chemists, and they are working on that, which I'm going to talk about today, about this metal boron compounds. And this carbon, another field which is a carbon boron is carborane, also very important field, and a class of scientists are working on this type of compounds and their application in BNCT and other therapeutic application. So as I said, that compound having a metal and boron is called inorganometallic chemistry, or which is quite resembles to the organometallic. Not only that, actually people prove it, how they are correlate to each other, right? So here I have shown few of the examples. Here in the right hand side, you can see the iron olefin complex, which is an organometallic compound complex, and similar iron boron compound has been isolated and structurally characterized, which is analogous to this iron olefin complex. Metallocene and the ferrocene, which is very well known and very much important in organometallic chemistry in the catalysis as well, the similar type of structure has been synthesized in the metal boron compounds and structurally characterized in using iron, cobalt, and ruthenium. The pentylene, the ruthenium analogs, has been synthesized very recently in 2005, and they have shown that how the organometallic chemistry and the metal boron chemistries are very close to each other. So the question arises how we can synthesize these type of metal boron cluster compound. And after extensive study, they found that metal polychloride can be very important metal precursor to synthesize these type of metal boron compound. So when they use this metal polychloride react with the lithium or sodium borohydride followed by BS3 as a source of the hydrogen, what they found is metal boron compound. With the elimination of the boron leads to metal hydride, and which is only depend on the metal center, which metal are you using, which actually directed or the lead to the product. If there is an elimination of the hydrogen, it gives the metal boron compounds. If you see in the literature, the late transition metals, which are very much rich in the electrons, having the metal boron clusters are very well known and well reported. But early transition metal, there are very few examples are known because the metal itself having the deficiency in the electrons. So they are less prone to react with the electron deficient boron. But what we have done is that we took this tantalum precursor, polychloride, and reacted with lithium borohydride and BS3, and we could able to isolate the very sensitive, air insensitive, this tantalum boron compounds. Here you can see their geometries are really, really unique. They are unknown, and if you can correlate with the organic compounds, then we can definitely talk about that or describe that. This guy in the middle having the B4H10 is basically bicap tetrahedral structure, and this tantalum B5H11 is, you can imagine, of one missing vertex having the hexagonal bipyramidal geometry. The top guy is having a very unique geometry, which we can derive from the dodecahedron, and via the removal of one of the vertex, the 5 connect vertex, which give this nido tantalum Cl2B5H11 tantalum boron compound. Not only we restricted to the tantalum, but also we explore the vanadium and niobium, and we got this structurally characterized metal-metal bonded bridge between the hexa B2H6 moieties. And after synthesizing a series of this group 5 metal boron compounds, we also were interested to explore their chemistry and their application. In that, what we found that this tantalum B5H11 is basically able to activate the hydrocarbon. If you just take the benzene or toluene and chlorobenzene and thermalize it, what we can see that one of the CH bond of sp2 hybridized CH bond has been activated by this cluster compound, which we have isolated and characterized as well. So we were very delighted that this metal cluster compounds is actually having a lot of potential in different applications. So this part I'll just mention because we all know about the isolable theory, and which was given by the Hoffman, and he got the Nobel Prize in 1981 because of the importance. This isolable theory actually brings the organic and inorganic chemistry into the same stream, and you can mix up the reactions and leads to a novel hybrid compounds. Where in definition, the isolable fragments are those which having the approximately same energy, same number of electrons, and having a same symmetry, which those fragments we call this isolable. Like BH fragment is isolable with the CH positive. And using the same phenomena, when we reacted with this Fe2CO9, we could able to isolate this cubane type of metal boron clusters. And we have characterized it and isolate, and you can see this unique structure of the metal boron compounds having the ruthenium as well as iron. And we have characterized with multinuclear NMR, boron proton 13C as well, and which shows the unique reactivity or the using of this isolable theory, which leads to a unique structure as well. Okay, so from this, I like to move on my second part, So the metal cluster the chemistry is not limited what I have shown. A lot of researcher in this world are working on that and then looking for the a novel, unique bonding as well as the geometry of these type of cluster compounds. But now I'll just take you to the another part which we call is organoborane compounds. Organoborane compounds nothing but having a compound having the direct carbon boron bond. And I'll just talk about their application as well. So this organoborane chemistry starts sometime in 1950s. H.C. Brown, who was a professor in Purdue University in US, he got a very brilliant postdoctoral student in 1950 from India. And he particularly mentioned in his Nobel lecture about his student, Dr. Subbarao, and his contribution. What student found is that when they took this very reactive, this BS3 reactions, as we saw that they have an outer shell only 6 electrons, they are very reactive. When they reacted with the unsaturated CC double bond, what they saw that BH bond is adding to the CC multiple bond in syn way, and which leads to the carbon boron bond, which can oxidize it and convert into the terminal alcohol, which was the main challenge during that time. So this reaction got so much of attention because the reaction was very fast, and the addition was anti-Markovnikov, and the addition of the BH bond is the syn to the CC multiple bond. So you can add not only CC double but also triple bond as well. More importantly, once you have this CB bond, you can convert this CB bond into different functional group. You can convert this into the alcohol, amides, esters, and halide as well. And that is the reason that H.C. Brown got the Nobel Prize in 1979 for his finding, which was published in sometime in 1952, first time. But as I said that whatever the reagent they have used is very reactive, right? So you need to maintain the inert atmosphere to do the reaction, but the organic chemistry don't like this inert atmosphere. What they try to find it out, why don't we use a more stable boron reagent? In that connection, they got that if you synthesize or get this bisphenolic diborane, this diborane reagents, here you can see this called as a pinacolate because it has a pinacolate back bonding. Similarly, B2-Cat2, which we call the bis catecholato because it has a catechol back bonding and this neopentyl back bonding. So these 3 diborane reagents were very stable and you can easily synthesize in the lab. And more importantly, now these diborane reagents are commercially available. More or less all the big chemical companies, you can order these diborane reagents. And the reason behind the stability of this diborane was the oxygen atom, which is next to the boron, which we all know that it has an extra pair of electrons, which it gives its extra pair of electrons to empty p orbitals of the boron and stabilize the boron. And because of that stability, this diborane reagent, you can handle it in air. But those reagents which H.C. Brown has been used, you need to handle in inert atmosphere, in nitrogen and organ atmosphere, and they are pyrophoric. You just open it, it will catch the fire. But these diboranes are very stable. But later, the chemists found that there is a limitation. This boron becomes that much stable that you cannot just simply add on the organic unsaturated substrate. So you have to activate this BB bond. And towards this, what they found is, if you use a metal as a catalyst, you can do that. Here I have shown one of the examples. When they use a platinum 0 complex, this diborane is oxidatively added to the platinum center, and which has been transferred to the CC triple bond by the insertion reaction, and elimination leads to the addition of this diborane to the CC triple bond substrate. which gives this organoborane compound. So this is another way to synthesize the organoborane compound, which Axi Brown has been invented. But the reaction is quite complementary to the Axi Brown way, and unreacted alkane or alkene arenes are also been able to the boron can be introduced in this type of reactions. Okay, so there is a other way also. You just take the organolithium reagent or Grignard reagent and react with the suitable boron reagent. You can get this organoborane compound, and people are doing that, organic chemists particularly. But it has some drawbacks. The drawbacks are you need to maintain the low temperature, like -70, using the liquid nitrogen or so. And these reactions are very air and moisture sensitive, and they are having a lack of functional groups. So using the metal as a catalyst become a major breakthrough in this field in the organoborane synthesis, and people use precious, non-precious metal. Here you can see the rhenium and iridium can directly activate the CH bond of the alkane and the arene CH bond as well. And it has been highlighted in several times. Okay, but why we need to synthesize this organoborane? So there should be some application. And here comes the CC coupling reaction. The Suzuki has invented that when you take this organoborane, or we can say organoborane acid or borate ester, react with any of the alkyl or aryl halide using the palladium as a catalyst, they can actually couple. Because in organoborane, this carbon having a partial negative charge, and whatever the aryl halide, the carbon is partially positive. So positive and negative can come together and make the bond. And that this reaction become that popular that the Suzuki shared his Nobel Prize in 2010 with the Heck and Nigishi. And the reaction was that popular. The reason was only the organoborane compounds, which you can synthesize in very economic way. And lot of pharmaceutical, agrochemicals, and in the material industries, it took this CC coupling reaction, and they have synthesized a series of the compound. As here, I can show that this organoborane compounds, you can synthesize a series of organoborane compounds, not only the sp2, but also the sp3 CB bond, and as well as sp CB bond organoborane compounds, which can easily couple with your desired alkyl halide. So if you see the mechanism of this reaction, particularly Suzuki-Mura cross-coupling reaction, this aryl halide will first go to the metal center, palladium 0 center, in oxidative addition, which gives this convert this palladium 0 to +2, and then the transmetallation steps comes, which brings the another coupling partner to the metal center, and followed by reactive elimination reaction give the CC coupling product. And here you can see this organoborane coming to the picture in transmetallation steps, and this has been widely used because it's a mild organonucleic acid. They are very stable. You can do the column, or you can synthesize in air in presence of moisture as well. And you can handle very easily, and they are less toxic. And toxicity is very much concerned in the pharmaceutical industry, because when you take any of the medicine, not a trace or the ppm level of the impurity of the heavy metal should not present. So in that case, what they found that this CC coupling reaction is very useful. And here I have shown one of the example, this losartan, which is an anti-hypertensive drugs, usually used by the person who is in depression or having anxiety or so. So this molecule you can easily synthesize once you have this organoborane compounds coupled with your coupling partner and keep the 93 very high % yield. And that is the reason the price of this molecule or the medicine become very low, and very normal people can afford this medicine. So that is the reason that organoborane becomes so popular, and a lot of researchers are interested to synthesize that. Not only that, some boron containing bioactive molecules are also known. So here I have shown some of this anti-cancer therapy. These boron compounds are in the market, and some of them are in the advanced clinical stage, and which soon will come into the market. For type 2 diabetes, also the boron containing bioactive compounds are in the market, which has been used for the type 2 diabetes. For antifungal agents, also the compounds having the boron moiety are present in that. As a synthetic chemist or inorganic or organic chemist, we are more interested that if you have one compound, can we derivative it? Can we functionalize it? So in that case, this boron or organoborane or aryl boronic esters, you can see that you can convert into different functional groups. You can convert into the halides, alcohols, acids, cyanide, uh, ethers, amides, and CC coupling products. So knowing all these applications, the CC coupling, functionalizations in therapeutic, in agrochemicals, in material, on OLEDs, a lot of researchers were working on the synthesis of these organoborane compounds. And if you see in the periodic table that the precious metals like rhodium, iridium, palladium, platinums are very much explored as a catalyst to synthesize these organoborane compounds. But our intention was to use very cheap first row transition metals because they are very cheap, earth abundant, and environmentally friendly. So I'll just show that what is our discovery and what we have done. So here I have divided in two parts. One is the homogeneous catalyst system and the heterogeneous. So first, very briefly, we'll see that how this homogeneous catalyst system can be used for this organoborane synthesis. So the first target molecule was alkyl boronic esters having alkyl groups. And they are also very important in medicinal chemistry as a versatile intermediate for CC coupling reactions. And you can definitely synthesize in other way. Like, as I said, the alkyl lithium or Grignard reaction, you react with the particular boron reagent, you will get it, but they have a limitation. We saw that. Hydroborations of alkene is another way. Beta borylation is another also very good tool, and CH activation as well. But most of them are using precious metal as a catalyst for the synthesis. The recently direct CX carbon halogen bond like bromide, chloride are coming to the picture that you can particularly introduce your boron to a particular position where the halogens are. And for that, cobalt, copper, palladium, and nickel has been used. So here what I'll show is alkene hydroboration, CX activation, and the beta borylation we have used for the synthesis of organoborane compounds. Initially, we have successfully used a homogeneous catalyst system. This is zinc as a catalyst and the copper as a catalyst to synthesize this organoborane derivatives, and have published in a range of papers. And it has been cited very well. But I must add here that homogeneous catalyst system has some limitation that we cannot recycle the catalyst. So when we look that whether heterogeneous catalysts can be used for this type of transformation, then we found that there are some reports, a few, for the hydroboration, CH, hydrosilylation, CX activation for this type of the organoborane synthesis. But as I mentioned that we are looking for the alkyl boronates, and in that case, we found that only two heterogeneous catalysts, the copper nanoparticle and copper +1 oxide has been used for this transformation. But the limitation was the alkyl halide was only the bromide. So the substrate scope was very limited. We would like to expand it with the chloride because alkyl chlorides are very cheap substrates. And using this iron supported copper nanoparticle, which has been characterized very well in the different spectroscopic method, we found that we actually can activate this alkyl halides. After a range of reaction, we found that the best condition can be used using potassium tetrodoxide as a base in DMF as a solvent in 18 hours can easily convert in this alkyl halide to the alkyl boron ester in quantitative yield. And then here you can see the substrate scope, not only the primary alkyl bromide, but also the secondary alkyl bromides can also be borylate and can give this alkyl boronate esters in good to excellent yield. As I said, the main target was alkyl chlorides. So we could able to do that using our catalyst, the heterogeneous catalyst. And here you can see we have borylate a range of alkyl chlorides in good to excellent yield. Not only this bis-phenolated diborane reagent, but this bis neopentylated diborane reagent also can be used for this transformation, which was really good. And we know the heterogeneous catalyst has a very important benefit in compared to the homogeneous is recyclability. So here you can see that we can recycle our catalyst up to 10 cycles without any loss in the activity. And very simply applying the magnet, we can recycle that. And you can see the recyclability was really great, and mercury poisoning experiment proved that the catalyst is actually heterogeneous in nature. We also would like to find it out what may be the possible mechanism of this transformation. So for that, we took this 6-bromo-1-hexene as a substrate, which is very well known that if there is a radical around in the reaction, it will go to the cyclization reaction. So using this substrate, we found that in our case also, we got the cyclized product, cyclopentyl methyl prepene product, which shows that that reaction is probably going via radical mechanism. And similarly, when we use this cyclopropyl methyl bromide, we got this ring opening product exclusively. Further, we support that when we added in the reaction mixture, this radical scavenger 9,10-dihydroanthracene as an additive, or radical scavenger, or TAMPO as a radical scavenger, it stopped the reaction, which confirmed that this reaction is going radical mechanism. So not only the alkyl halide, but also we can synthesize this alkyl boronate ester via this alkene hydroboration as well. So after extensive screening, we found that using methanol as a hydrogen source in DMF at room temperature, we can actually hydroborate a series of terminal alkene as well as the internal alkene, which gives this alkyl boronate in good to excellent yield. Again, we would like to know the mechanism, and this reaction also turns out to be a radical mechanism, because when we use this this vinyl cyclopentane as a substrate, which goes to the cyclization product again, which has been confirmed by the spectroscopy GC-Mars and proton NMR and 13C NMR spectroscopy. So which shows again that this might again going via radical mechanism. And when we added this 9,10-dihydroanthracene or TAMPO as a radical scavenger, it stopped the reaction. Also, we would like to know that whether or not in situ, because we are using methanol and DMF as a solvent, whether B2P2 is converting in situ to the HPP, which can directly add to the alkene to make the hydroborated product. But when we use the HPP as a boron source, we did not see any product, which eliminate the possibility of formation of HPP as an intermediate. So next class of the substrate, what we have used it is alpha beta unsaturated carbonyl compounds, and using potassium carbonate as an activator, methanol as a hydrogen source, we could able to introduce the boron at the beta position using B2P2 as a boron source and this ion supported copper as a catalyst. And here you can see a range of this alpha beta unsaturated carbonyl compounds has been borylated and giving the yields in excellent, good to excellent yield. So needless, I want to mention that all these compounds has been isolated chromatographically and characterized by the multinuclear NMRs like proton 13C and boron and the GC-mass and HRMS as well. So the next few minutes, what I'll show that not only this alkyl halide boronates what we have successfully synthesized, but we can able to use our heterogeneous catalyst system for carbonyl reduction as well. So if you see this carbonyl C double bond O bond can be reduced and hydrolyze and oxidize and give the alcohol. You can simply use sodium borohydride or lithium aluminum hydride to do that. The problem was the functional group tolerance. You cannot reduce such type of carbonyl compounds which having the irreducible like alkene or cyanide and nitro groups. So for that, this metal catalyzed selective reductions come into the picture. And if you see in the literature, the transition metals, main group, and F block element has been very much explored for this type of metal catalyzed carbonyl reduction followed by the oxidation which gives this alcohol. But this homogeneous catalyst systems has some limitation, and also we were particularly interested in iron, and because they are less toxic, they are environmentally more acceptable and low cost, of course, and they are abundant, right? And in homogeneous catalyst system, this iron catalyzed are few reports were there when we started our work, and but we know that homogeneous catalyst system has some limitation. We need to maintain the inert atmosphere, and final product may have the metal contaminations and lack of recyclability, of course. So the reusable or heterogeneous catalyst system also has been used for this carbonyl reduction, but particularly MOS supported or copolymer supported metal catalyzed carbonyl reductions was known. But metal oxide or metal nanoparticle catalyzed carbonyl reduction was not known. So toward this, after screening, we found that this Fe2O3 nanoparticle can be used for the reduction of this aldehydes and giving this alkyl boronic ester, which can easily convert into the primary alcohol. And here you can see the range of aldehydes has been converted into the borate esters and converted into the alcohols. Not only aldehydes, but ketones also can convert into the boric esters and secondary alcohol using our catalyst. And more importantly, we can do this reaction in gram scales. Here I have shown the three examples where three substrates has been converted into the gram scale primary alcohol, and which shows the compatibility of our catalyst system. As I said, that the metal catalyzed carbonyl reduction is very much explored or found attention. The reason was selective reduction. So we also want to find it out whether our catalyst is selective or not. For that, we first found that our catalyst is very selective towards the aldehyde reduction in compared to the ketone, as well as when you have intramolecular reducible functional groups like ketones or ester or amides, it reduces specifically this aldehyde CO double bond. And on the electronic effect also, we have found that electron deficient substrates are faster than the neutral, then followed by the electron rich substrate. So the mercury poisoning experiment shows that which heterogeneous chemists are using the mercury, because it actually blocks the active side of the heterogeneous catalyst, and if it is blocked and if it is heterogeneous, then the reaction may not go further. And using the mercury, we found that it is heterogeneous in nature. Recyclability shows that it is good. The catalyst is quite up to 4 cycles recyclable. But after that, we found that there is the reactivity has goes down. But when we recycle after the fifth cycle and activate the catalyst, we can actually get the comparable yield. And that was the great that we can actually reactivate our catalyst if it is the activity has gone down. Also, we try to find it out what may be the possible mechanism, what is the interaction between our heterogeneous catalyst and the substrate. So we found that there is some interaction between the substrate and the catalyst, heterogeneous catalyst, which we found it via the ion spectroscopy, which shows that there is the shift in the lower wave number when we mix this iron Fe2O3 and the substrate benzaldehyde, which shows that there is some interaction between the substrate and the catalyst. Also, we expand or extend our this iron oxide nanoparticle catalyzed carbon reduction to the F block element. And towards this, we found that cerium dioxide nanoparticle can easily reduce this carbonyl aldehyde ketones in very efficient way. If you see in the homogeneous catalyst system, there are reports where this F block element or F block complex has been used as a catalyst for the carbonyl reduction. But here you can see this all catalysts need to be synthesized in multi-step. And for the synthesis, you need to maintain inert atmosphere. But in our catalyst, the cerium dioxide can be synthesized very easily and without using any inert atmosphere. And using this catalyst, we can produce this aldehyde, a range of aldehydes, not only aldehydes, but ketones, which gives the excellent yield of the borate esters. And also, we recycle the catalyst, and we found that up to almost 10 cycles, the activity has not gone down drastically. And again, we after the 10th cycle, we separate the catalyst, we calcinate it, and we use for next cycle, and we found that it is reactivated and given the comparable yield. And there is no change in the morphology of the catalyst as well. And the mechanism shows that there is an interaction between the cerium dioxide with the substrate, and followed by HPP, probably sigma bond metathesis reactions, which gives this borate ester with the presence of another molecule, which gives the borate ester and recycle the catalyst. So I hope that from this, I would like to summarize that what we are exploring currently, the heterogeneous catalyst system for the synthesis of organoborane compounds. And towards this, we have successfully synthesized this alkyl boronate esters via the alkyl halide, CX activation, hydroboration of the alkene, and the beta borylation of alpha beta unsaturated carbonate compound. Also, we have shown that the heterogeneous catalyst can be used for the carbonyl reduction as efficient like a homogeneous catalyst system. And these are the two examples where Fe2O3 and cerium dioxide has been used for this carbonyl reductions. Okay, from this, I'd like to thank my co-workers, and all credits goes to them. The most of the work has been done by my first PhD student, which is basically recently graduated, Dr. Mahadev, and some of the parts has done by Mr. Ramesh, which is currently doing his PhD in our lab. And the funding from the SCRB, startup grant from the chain, my collaborator from Germany, as well as ISC. And I would like to invite you in our center. If you get chance to visit Bangalore, please stop by. So it's a bit far from our city center, but it's in Kanakpura Road, but it's very nice campus. And we are situating in the 4th floor, where the 4th floor is totally dedicated for our center and our research. It is almost 11 years or 10 years old, our center now. In 2012, it has been established. From this, I like to thank all of you and thank you again, the organizing committee, for giving me this opportunity. I will be happy to answer if you have any questions. Thank you.
Sir, there are some questions.
Yeah.
Sir, the first question is from Pavitra Samaje. Sir, the question is how boron could be more selective towards cancer treatment?
Uh, yeah, that's why I have shown that there is a limitation that how you can introduce this boron into a particular cancer cell. So what people are doing is they are enriching with the B10, the carborane compound, and they are hooking with the amino acid, and that amino acid they are transferring or the injecting to the human body, which is more affiliated towards that amino acid is more affiliated towards the cancer cell, so that that amino acid can directly go to the particular cancer cell. Once it reach, you can actually apply this thermal neutrons externally, and by that you can particularly destroy the cancer cell. So as also I mentioned that the chemistry part is fine. The problem is how you will introduce this boron rich compound to the particular cancer cell. But once it reach, you can destroy very specifically, because the energy what is produced by this the splitting of the B10, which gives this helium and lithium particle, is that much only that it can just destroy the diameter of that cancer cell, so it won't come out. Yeah, I hope that I answer your question.
Okay, sir. Sir, one more question.
Yeah.
From Purushottam, sir. That is borane, carborane, metalloborane, and metallocarborane. Which one is more stable?
See, in this, as you asked, the metal borane or carborane, more or less all are stable. Unless otherwise the compounds are not stable, you cannot isolate it. And here you can see that I have given one example as well, that we reacted with tantalum polychloride with some boron source. As I saw that this is a kind of metathesis reaction. This boron reagent, what we are using, it will add up and it will reach to the particular geometry where this compound or the molecule becomes stable and reach to the stable configuration or electron counts. Once it reach, it is, you can isolate it. So coming back to your question, the carborane are more or less as stable like metal boron, but metal boron compounds are not that stable. You have to keep in an atmosphere. But carborane, again, the sum of the carboranes that like decaboranes and 12 vertex icosahedral carboranes, they are quite stable. Yeah. I hope that I answered your question. If any further question I would like to, I'll be happy to answer them.
Sir, one more question, the last one. As we have proton NMR for the identification of number and nature of hydrogen molecules, so do we have any particular technique for identification of boron compounds?
Yeah, absolutely, it is there. And I have mentioned, probably I forget to mention that all the boron clusters and even the organoborane compounds, there is a boron NMR. Similar like a proton and 13C, boron also a NMR active nucleus. But as I said, that boron has two isotopes, boron 10 and boron 11. But boron 11 is more abundant, 80%. So the boron 11, you can easily find it out. Even you can quantify how many borons are present in the particular pure compound. And there's a lot of literature, and even Lipscomb has done a very nice work on the boron NMR as well. So yes.
Thank you so much, sir. I request all the participants that feedback link has been shared in the WhatsApp group. So I request all the participants to give your valuable feedback. Now I request Professor N.B. Gokavi sir, Head Department of Chemistry, to present a vote of thanks.
Good afternoon, everyone. Respected dignitaries of the today's national webinar, I would like to propose vote of thanks. At the outset, I am grateful to Dr. Subhankar Kumar Bose for accepting our invitation in spite of his busy schedule and enlightening us with his knowledge. This will help us in our studies and future. I thank you very much, sir. I am very happy thankful to our principal for her gracious presence and constant support in conducting his webinar. I also thank Dr. Satisha MP, coordinator, IQAC, K.L.E. Society Life member for his support for conducting the webinar. I also thank our webinar committee who are really worked hard to make this event successful. Last but not least, I thank all the participants and students for paying their attention and making this webinar is meaningful. Thank you one and all.
Yeah, thank you, sir.
Once again, I would like to say thank you. Thank you for the participants and thank you for today's resource person. Thank you, everyone.
Thank you, sir. Mute ಮಾಡ್ಕೊಂಡು ಮಾತಾಡ್ತೀನಿ.